So this is stellar evolution. And the first thing that happens is that a cloud of mostly hydrogen gas, but there can also be just sort of other debris, collapses, right? So there's this notion that that a cloud has its own self-gravity, and that gravity is going to crush the cloud, right? And once it collapses, it's going to be on the main sequence for some amount of time, right? Although there are some giant stars there's just so much mass that it just explodes, right? So super giant stars, not necessarily, right? But this is a possible scenario. Then it's going to possibly be a red giant, depending on its size, and you'll learn that in the little stellar evolution flowchart that you're going to do, right? Especially the Chandra site. If you go there, you'll see this, right? Okay. And so let's protostar, right? And then its main sequence. You could make like your own timeline, right? Okay. Then it could be a red giant. This is the most exotic thing, right? Okay. Then it could become a white dwarf, right? Or it could actually supernova, right? Okay. And when it supernovas, it could then become a neutron star, right? Neutron stars are also pulsars, right? Okay. Or it could become a black hole. Okay. And black holes could be quasars. Not all black holes are quasars, but that's what quasars are. They are black holes that are like where there's material falling into them. Yeah. Right. So this is kind of the general over thing of what we're going to do, right? So the protostar, basically, you've got this cloud of stuff, right? And it's going to collapse because its own gravity is going to crush it, right? All of this force is going to act this way. And I had this beautiful interactive physics. Simulation of this. It showed it collapsing. And one of the things it does is if there's any rotation in this cloud, when you collapse it, it becomes incredibly small. And when it becomes small, it spins very, very fast. Yes, sir?
Yeah, I got a question. Logger Pro, downloading it off the internet. Is there somewhere on the website where it says how to do it?
Oh, how to do it?
Yeah.
This is what you do. No, it doesn't, but that's you put that after the URL.
Just for near install.
Yeah. /V, capital I, no space.
Okay.
And it'll take you to it. You can download the thing, and then
You got that?
Okay. So here's the deal. Those gates at IBOC, right? When you sit on them, when you pull yourself to the middle when you're spinning, right? Have you ever tried to pull yourself really hard? Like, I'm going to get to the middle of this. Yeah. What happens? Can you do it? No, the world becomes a blur, right? You're just like, right? And it's like you're spinning like a bajillion, and then you realize you're sick, right? Yeah. And you kill a little grass around there or something. I didn't actually get sick, but it did something to my inner ear with that thing, right? Okay. And so basically all there has to be is like a knot, just a little thing that's more dense than the surrounding. Everything's going to collapse on that. But the problem is that once it collapses, it's often spinning way too fast, right? So this is, and there's my demonstration that no longer works, right? Okay. The rotation becomes, a small rotation becomes a big rotation. And it's that same thing. We don't even need to if you pull your arms in or you pull yourself into the center, you go faster and faster, right? And so the question is, and the problem is that when they set these things up, they would model these nebula collapsing, and they always spun too fast. Every nebula that they could computer model spun too fast. Therefore, stars could never be born. This was a sort of a scientific crisis, right? It's like, oh, stars can't be born. Almost any cloud of gas has enough spin to it that it can't actually be born, right? And so they look for a mechanism, and they realize that these things have strong magnetic fields, and that these magnetic fields tend to, once this collapses, right, you've got this little disk spinning, the magnetic fields tend to jet material. These are called polar jets, right? They tend to jet material north and south simultaneously. And these are ubiquitous. You see these all over the place. You see them in quasars. You see them around neutron stars. You see them around white dwarfs, right? But anyway, yeah. And here are some pictures. This is a picture, if you look up there. In the picture, right, see that little jet sticking out there? That's tens of kilometers per second. That's stuff shooting out in that direction. This is a visible one. This is one of the few visible jets I think that they've seen. They've got a bunch of them with like infrared that they've seen. The problem is that these jets are often happening inside nebula, so it's hard to see inside there. But there's a jet. Presumably the other side of this is somewhere deep in this nebula, right? See this thing that looks like a little lump? That's exactly what it is. That's something about the size of our solar system that possibly is a protostar. This pillar right here is also probably a solar system that's formed. And the reason that it's still there, there's a star, a giant star. Matthew. There's a giant star up above here that we can't see. It's out of the view, right? That's blasting this thing here downward. Any place that's dense is protecting the stuff below it. So this is actually a pillar. That's not a jet. This thing is a jet, though. It's long and thin like that, right? It's got little sort of bumps on it like that, right? So that's what jets look like. This thing's a pillar. This is a giant pillar right there, right? Okay, so yeah. There we have it, right? So that what they think is what happens is that it loses its spin by shooting stuff off that's spinning faster than it. Yeah? Can't do that at IBOC, but if you could, why it would work, right? If you could somehow shoot material that's spinning the same way you're going and get rid of it, right, then you would spin slower, right? Eventually, when it collapses, right, what you need for fusion is you need heat and you need pressure, right? Because fusion is between two positive, basically it's two protons have to get close together, right? And there's a whole cycle, it's in your notes there. Right? But if you can get two protons together close enough, they'll bond to each other and release nuclear potential energy, right? But what's the problem with getting two protons close to each other? It's hard. Why is it hard? They repel each other. Two positive charges repel each other powerfully, right? And you've got to get them really, really close, right? So you've got that repulsion. So heat works because when something's hot, they're moving fast, and if they move toward each other, they can't stop in time, right? And they fuse. Pressure works because in a really high pressure situation, they're just closer to each other, right? So you need heat and you need pressure, right? If you increase the heat and pressure, you'll increase the rate of fusion, right? The other thing you need, and it's not really in here, but did you guys learn about the Heisenberg uncertainty principle in chemistry? Anyway, things that are this small actually don't obey conservation of energy, and so one of the things you also need is luck, right? Right? There's this random variability, and things can just magically get from nowhere energy that they don't have briefly, right? They have to pay it back in the long run, right? But they can just briefly borrow energy from the vacuum, and it turns out you need a lot of that to get our sun wouldn't work without luck, without Heisenberg uncertainty, right? So anyway, what happens then is you get this sort of an accretion disk, which looks like the rings of Saturn, right? Okay. All of this nebula, when it comes in, it's spinning, and it basically just adds up, and you get only one plane of rotation, right? And the reason for that is that if you've got a disk, I need a disk. Here's a disk, right? If you've got a disk like this, a disk, right, that's spinning, everything's going to add up and eventually be on one plane. If you've got something that's going like a Pluto orbit, right? What's it going to do when it hits the disk? Isn't it just going to add to the disk, and then the disk might shift a little bit, right? So that's what happens is eventually you get a disk-like accretion of matter, because anything that's off the plane of the disk hits the disk and just joins the disk, right? Okay, gravity does that. So the rings of Saturn, that's a normal thing, right? So picture the rings of Saturn around the star. You've got this accretion disk. You've got the star in the middle like that, right? Okay. Only it's not Saturn, it's the sun. Here's a picture right here. This is 500 astronomical units, so that's sort of like a solar system-like distance. And here's an accretion disk that happens to lie right across the plane of the new star. So there's the new star. There's the accretion disk right across it, right? So you can see these all over the place. We can't see what it looked like when our solar system formed, but we can see solar systems forming in distant nebulas, which is kind of cool. Isn't that cool? Is that cool? I don't know. Right? Not so much right now, but thanks.
I was wondering
Okay.